recording. Okay, so today we're going to finish chapter 4, and we're going to be doing this by talking for 7, for 8, for 9, and for 10.
410 is the bit on history, right? Exercises is like 411, which we're gonna skip.
Yep, yep. Is this correct? For
You're
6?
scrolling, yeah, you end up to 46.
No, yeah, but I was pretty sure that we are missing a chapter here. Where is the Haskell chapter?
It's 48, I think.
Oh, okay. I was very sure that was the other way around, but okay. I think in the new version it is actually.
Huh. Man, every time you pick up that book on camera,
Yeah, it
I'm
is.
amazed at how large it is.
It is. 4-7 is Haskell in here.
Ah, okay, so they flipped the order in the new edition. That's
Yeah.
interesting.
Yeah, and just for the record, we are here. So the last fat is what we read.
Yeah, that's about slightly more than a third of the book, I guess.
Yeah, slightly. Actually, more like exactly a third. We are on page 345 or 50 or whatever. Okay, so it's the other way around. Good to know. Anyway, so let's start. So limitations and extensions of declarative programming. Poggers to the book because it's basically saying that it's acknowledging that even though it's cool and impressive that we can have declarative concurrency, the word is not declarative.
Yeah, there are some things you can't do unless you step out of this model.
Yeah. Well, it begs the question if all the situations we need to get out, step out of it. The answer probably is no, but for a lot of different reasons we end up doing that. So let's read the questions. Is how far can declarative programming go? Can everything be programmed in a declarative way such that programs are both natural and efficient? And then we're going to define what those terms mean. So efficiency, we say that programming is efficient if its performance differs just by a constant factor from the performance of an assembly language program to solve the same problem. So like we are not handicapping the performance of the program because of the way that we are writing it. And we also say that a program is natural if very little code is needed just for technical reasons unrelated to the problem at hand. So this is essentially you're writing
You don't have,
code that is directly related to the problem and not code for related to other things.
yeah, you don't have to do any juggling of technical details that you don't wanna care about, right? Like the case of that buffer example. It's
Mm-hmm.
actually where the first version is like, okay, here's how you'd have to do it if you have to program the laziness by hand, and it's very
Yeah.
ugly, right?
Yeah, I think this thing is kind of complicated because a lot of the time, especially if you are like writing a library, for example, you are writing code that is not related to a particular problem, but you may be writing code that is related to a class of problems. Uh, but from the perspective of the user of the library, it doesn't matter how unnatural that code is because you're just going to call the library anyway. So this naturality point is kind of blurry to me because a lot of the time, if you're making code in a library, it's not going to be natural for the if somebody is reading it aside from the library developers. So, but I would say this is a fair point anyway. It's just that we need to take that with a grain of salt. So efficiency. So the quick version is no. It is not efficient to do that. So
Uh, yeah, I
there is
mean,
a fundamental mismatch between the declarative model and the standard computer. Uh, the computer is optimized for modifying data in place, where the declarative model never modifies data, but always creates new data. And then, if we stop right here, somebody can say, well, we can make smart enough compilers
Actually, you would have to solve this by changing the runtime. The compiler is not enough, actually,
The runtime of what?
of the language that you are compiling to. Like, for instance, there is research around doing opportunistic mutation by
Yeah, yeah, yeah,
using reference counting,
yeah.
but that requires your runtime to do reference counting, right? Which it may not want to do for
When I
one
say the
reason or another.
compiler, I'm also talking about the runtime. Like,
Oh,
to me, the
that's
compiler is the
fair.
entire thing.
Oh, that's fair.
Um, so yeah, this is not as severe as a problem as it seems at first glance. The declarative model may have a large inherent memory consumption, but its active memory size remains small. We've seen this before with a numeric example. The task remains, though, to implement the declarative model with an in-place assignment. This depends first on the specification of the compiler. So, like, there is a certain amount of ground that you can cover by making the compiler smarter, but we have very limited um, in terms of the ambition. We are very limited. The compilers are not that freaking genius. Like, at least in my experience, the cleverest compiler I ever worked with was Rust's. It's very impressive what the error messages from the Rust compiler. It can tell you a bunch of like very non-trivial suggestions on how to fix your code. So that's a step in the right direction, but I still think that if we want to go full like no compromise, we are very far away from that.
Yeah, I think the closest thing we have at the moment is Rock, which does actually uses the reference counting thing I mentioned. But the problem with reference counting is okay, but now you can't have cyclic data. So now what?
Yeah, you gain some, you lose some. Paraphrasing science fiction author Clarke, we can say that any sufficiently smart compiler is indistinguishable from magic, which is very true if you, for example, when working with Rust. That it is unrealistic to expect a compiler to rewrite your program. Even after several decades of research, no such compiler exists for general purpose programming. The farthest we have come is compilers that we can rewrite the program in particular cases. Huda calls the smart ALEC compilers. Because of their unpredictable optimizations, they are hard to use, and they increase the time of compilation. Therefore, for the rest of the discussion, we assume that the compiler is a straightforward mapping from the source program to the target, in the sense that the time and space complexities of compiled code can be derived in a simple way from language semantics. Um, so yeah, now we can answer the question whether the declarative program is efficient. And then, like I said, the pedantic answer is no. But in fact, the practical answer is yes, with one caveat. Declarative programming is efficient if one is allowed to rewrite the program to be less natural. So like, it's gonna look worse, but will to practically do the job. Um, a program that does incremental modifications cannot be cannot in general be compiled efficiently, and that's an example. However, if one is allowed to rewrite the program, then there is a simple trick that is often sufficient in practice. If the state is threaded, and the program is careful never to access the old state, then the accumulator can be implemented with this structure of assignment. We also have memorization.
Yeah, yeah. About that first point, there's a lot that you can gain by using the right data structures, but like most of the time, imperative mutable data structures they tend to have like constant factors for their primary operations, like arrays, for instance, right? Indexing is constant time, and so is updating an index in place.
Well, but
Um,
you can also
but then
do
it,
appending of different with using different lists in constant time.
yeah, but a difference list enforces a particular usage strategy, right? It doesn't, it can't, you can't do updates on a on a random element of the difference list, right? Once you
Yeah, yeah,
construct it, that's it.
it's not a one-to-one replication. But as you
And
said, you can go far, like a long way, but just by using the correct data structure.
yeah, but like even the best persistent data structures, they tend to be like logarithmic, which is not constant, obviously. So yeah.
Yeah. Same argument. Well, not exactly the same argument, but the accumulator argument appears again in the memorization. If you want to memorize it in a declarative style, you're going to have to rewrite the entire program, threading the accumulator everywhere. A function that implements a complex algorithm often needs intricate code. Even though the program can be written declarative with the same efficiency as a stateful program, does it so makes it more complex? This follows because the declarative model is less expressive than the stateful model. Okay, then we go to modularity. We see our program is modular with respect to a change in a given part if the language change can be done without changing the rest of the program. So this is the opera versus jazz argument from Hickey. Modularity is discussed further in the future. And then the memoization example. If you want to add an accumulator, we're going to have to rewrite the entire thing. And then the second example is instrumenting a program. We would like to know how many times some of its subcomponents are invoked. We like to add counters to these subcomponents, preferably without changing either the subcomponent interfaces or the rest of the program. Very similar argument to the memoization one. You're changing the functions type signatures. So you're going to have to rewrite every single callee and caller.
Yeah.
If program is declarative, that is impossible since the only way is to thread an accumulator throughout the program. So then we have an example of a module with a couple of procedures. You're going to have to add a new thingy. So in this one we have P1, and now we have P1, S1, Sn, and then we just increment the count. You're going to have to do that to all of them. So this is a pictorial representation. So this is essentially saying that the arrows that are bold kind of means that you're going to have to rewrite the place. And when using explicit state, you can see that you have very less bold things on the right.
Yeah.
And then the counterpart solution is using the stateful model, which is going to make the module an object. Like this. So you have something that is mutable going inside of the module, and you are controlling this by internally, and you're not doing that by using the arguments of the procedures, and you have an extra function to be able to look at it. So this is very like this is not an object essentially, using the definition
Basically,
from
yeah.
chapter 1.
Basically, yeah.
And all the bookkeeping is now being done internally, so that's kind of cool. What else is important to mention here? Yeah, this is explaining the figure that we just talked about. The declarative approaches are modular with respect to. Did you hear that?
Yep, it's thunder.
It's thunder. I hope I don't lose power. So if I lose power, we're gonna lose the recording.
That would be
The,
bad, yeah.
the declarative approaches are modular with respect to instrumenting P1 because every procedure, definition, and call on the path from main to P1 needs 2 extra arguments. The stateful model is modular because the cell is mentioned only where it is needed in the initialization of SC and in P1. In particular, the interfaces remain the same. Since the extra operation count can be ignored, all other components calling and cease do not have to be changed. Which approach is simpler, the first or the second? And then this is a very nice conclusion. The first is a simpler model, but a more complex program. The second has a more complex model, but a simpler program. So what does that even mean? This means that the mental model of the first is simpler. It has less moving parts, and it has more guarantees. But in order for it to be efficient, you're going to have to make it more complex, hence less natural. The
Not
second,
even not even efficient. In this case, you're adding an extra feature, right? So you're counting the calls when you're instrumenting like in the instrumentation example, right?
yeah, in the case of the instrumentation example, it's just talking about naturality.
Yeah.
The second has a more complex model, which means that it is more powerful, it has less guarantees, but the program, at least visually, is going to look simpler. I think it's very important to make this distinction because people usually try to mix the both understandings. One thing is how the program looks, another thing is how you understand what the program is effectively doing. Using a more powerful model, such as a stateful model, although makes the code looks nicer, when you have to read it and understand what it does, it's going to take a much more brain effort. Um, in our review, the declarative approach is unnatural because it is modular. The stateful approach is clearly the simplest overall. And then we have the fallacy of the preprocessor, which uses a very similar argument that I just described about what matters most is the mental model that goes in your brain. because
Yeah.
it's talking about using a preprocessor that can do the threading of the accumulator for us, so we don't have to write it ourselves. And why that doesn't work? That doesn't work because when using the preprocessor, you see only programs that look like the stateful version, stateful programs. This obligates us to reason in the stateful model. We have therefore de facto extended the declarative model with explicit state. So this is like just effectively, just practically. We haven't done that, but the preprocessor in conjunction with the declarative model will mandate us to think as if it was stateful, and hence we practically extend it. The
Yeah.
preprocessor transforms these stateful programs into programs with this threaded state, which are inefficient because of the all the argument passing. So there is a performance hit as well. And then we have non-determinism, which is also something that goes against the idea that everything can be declarative. Um, the model has a limitation that cripples it for many concurrent applications. It always behaves deterministically, and which is usually a good thing, right? We actually
Yeah.
see this more like kind of a positive thing instead of a negative thing. And
Well, it is negative in this context in particular,
yeah,
right?
in the sense of what can we do with it, it is negative because it can only be deterministic. If your program has observable non-determinism, then it is not declarative because the outcome is different. I
Yeah.
think this is a good reminder that declarative in this book means pure. So the same inputs, always the same outputs. And in this case, it's concurrent, which means that the order also doesn't matter, only the final output. This limitation is closely related to modularity. Components that are truly independent behave non-deterministically with respect to each other. To show that this is not a purely theoretical limitation, we have examples. So the limitation can be removed by adding a non-deterministic operation to the model. So like if we make it less well behaved, we can fix it. The extended model is no longer declarative. Um, so our first solution is to add a non-deterministic wait operation, such as wait true, which waits for one of two variables to become bound and indicates one of the bound ones. Its definition is given in supplement in the appendix probably. A second solution is to add isThat, a Boolean function that tests immediately whether the data flow variable is bound or not. This allows us to use data flow variables as a weak form of state, which we already concluded before, right? When we were talking about persistent data structures, we noticed that data flow variables is kind of leaking state information among the observers of the variable. IsThat is nice for the video. Oh, one of the applications. A third solution is to add explicit state to the model, which we're gonna do later anyway.
Actually, the next chapter even, we're gonna get into parts.
Yeah, chapter 5. So the first application is a client-server application, and here's our scenario. Assume that there are two independent clients and one server. Being independent implies that they are concurrent. What happens if they communicate with the same server? Because they are independent, the server can receive information in any order from the two clients. This is observable non-deterministic behavior, which is true. Let's
Yeah.
examine this closer to see why it cannot be expressed in the declarative concurrent model. The server reads inputs, an input stream. Uh, if it's one client that sends commands to the server, this works perfectly. How about when adding a second one? The second client has to obtain a reference to a stream that it can bind, and that is read by the server. The problem is that such a stream does not exist. There is only one stream between the first client and the server. The second client cannot bind that stream since that this would conflict with the first client's bindings. And then you may say, well, just have two streams then. Cool. Um, but
Yeah,
that
but
goes into a
now,
second problem.
yeah,
How
in which order do
in
you
which
read
order
them?
we
Yeah.
read them, right? And does it first read one element from the first stream and then one element from the second stream? Does it read simultaneously read one element from both? Neither of these solutions is correct. In fact, it is not possible to write a solution in the declarative concurrent model. The only thing we can do is to have two independent servers, one for each client, which also does not solve the problem because if you have a third server to like aggregate the information from the two servers, now you are back to square zero because now in which order the central server will read the information from the smaller two servers.
Yeah, or as the book says, the servers can just try to communicate with each other as well, and it also gives you back the same problem. So yeah, you're kind of stuck there.
Yeah. The simple answer is that the declarative concurrent model that doesn't fly. In the declarative concurrent model, an active object always has to know from which stream it to read next. How can we solve this problem? Adding non-deterministic into the things into the model, such as the wait true. And then we have the video display application, which what we're interested here is to skip frames, right? Because of the varying arrival rate, the displayer cannot always display all frames. For example, you might want to skip quickly to the latest frame that was sent. This kind of stream management cannot be done in the declarative model because there's no way to detect the end of the stream. It can be done by extending the model with one of the new operations. But this also goes into the same problem of like we can't do that. We must include this new operation that makes it the model non-declarative.
Yep.
And then we go to the final and most harsh conclusion. The real world is non-declarative. So this is very important because this completely makes the authors, in my opinion, more respectable because they are acknowledging that even though it's nice, we should not be religious about it. We acknowledge the non-declarativeness of the world. We acknowledge that. It has both state and concurrency. Since declarative programs interact with the real world, either directly or indirectly, they are part of an environment that contains these concepts. And then we go to the two consequences. Interfacing problems. Declarative components lack the expressivity to interface with non-declarative components. The latter are omnipresent. Hardware peripherals and user interfaces are both inherently concurrent and stateful. Operating systems are also concurrency and state for their own purposes because of the reasons mentioned previously. One might think that these non-declarative properties could be either masked or encoded somehow, but somehow this never works. Reality always speaks through. Specification problems. Program specifications often mention state and concurrency because they are targeted for the real world. Real world. If the program is declarative, then it has to encode this in some way. Yeah, so we have two problems. Things are often already non-declarative,
And you have to talk to them.
and things are usually also specified and detailed in a non-declarative way.
Yeah.
Picking the right model. There exist many computation models that differ in how expressive they are and how hard it is to reason about programs written in them. The declarative model is the simplest of all. But we have some limitations. There are more expressive models that overcome these limitations at a price of sometimes making reasoning more complicated. The more expressive models are not better than the others, since they do not always give simpler programs and reasoning in them is usually harder. Uh, yeah, there is a footnote here, but that's just a small detail. In our experience, all models have their place and can be used together to good effect in the same program. For example, in a program with concurrent state, many components can be declarative. Conversely, in a declarative program, some components need state to be implemented well. We summarize this experience in the following rule. When programming a component, the right computation model for the component is the least expressive model that results in a natural program. So there are two rules in here. How expressive it is and how natural the final program will look like. So that's two variables that you need to take into account. So maybe the least expressive model that is doable, it's to do the thing, is a declarative model, but it will make a very unnatural program. So you should take another model. Using a less expressive model will give a more complex program, and using a more expressive model will not give a simpler program, but would not give a simpler program, but make reasoning about it harder.
Yeah, I think this is a nice rule of thumb actually.
Yeah, this seems very intuitive. The problem with this rule is that we have not really defined natural. This is because to some degree it's subjective. Different people may find different models easier to use because of their different knowledge and background. The issue is not the precise definition of natural, but the fact that such a definition exists for each person, even though it might be different from different for different people. Yeah, this is very true, right? So um, the most like you, Mageta, and I, we always think like in a functional way, almost in a declarative way. We don't think in terms of the dataflow variables, but we try to make programs uh, as pure as they can be with pure
Yep.
functions and so on. But sometimes we break the rules. For example, in Karuta, we have an object in there, which is a PDL counter. It is an object now. Um, it has a stateful component to it. And I think, in my personal opinion, that is better than making it full declarative. Um, extended models. Now I have some idea of the limitations and a few intuitions on how extended models with stated concurrence can overcome these limitations. So now we're going to go through, we're going to name them essentially. So we have declarative sequential model, which is the first thing that we studied. The model encompasses strict functional programming and deterministic logic programming. So this is like ML.
ML, or I guess. Huh, I actually can't name a deterministic logic language off the top of my head. Like, most of them are actually non-deterministic. I guess Mercury, if you restrict yourself only to deterministic predicates.
I don't know, Mercury. Um, it extends the formal with partial values and a ladder with higher order procedures. Reasoning with this model is based on algebraic calculations with values. Equals can be substituted for equals and algebraic identities can be applied. Yeah, so it is referentially transparent. A component's behavior is independent of when it is executed or of what happens in the rest of the computation. Then we have the declarative concurrent model, which I have no idea of other language aside from OS that does this. This is a declarative model with explicit threads and by need computation. This model keeps most of the nice properties of the previous model while being truly concurrent. This model can do both
Uh,
data-driven and demand-driven concurrency. It subsumes lazy functional programming and deterministic concurrent logic programming. Components interact by binding and using sharing data for
I
values.
guess technically Clojure can express this if you restrict yourself to like not using atoms, but only delays and promises.
Mm, okay. And then declarative model with exceptions, which is just a contradiction because if it has exceptions, it's no longer declarative. Even though you can do a, a hack to make the exception handling keeping the declarativeness property. We've seen this example before. Message passing concurrent model. This is declarative model extended with communication channels, which is chapter 5, which we're going to read next. This removes the limitation of the declarative concurrent model that it cannot implement programs with some non-determinism. This is a useful generalization of the declarative concurrent model that is easy to program in and allows to restrict the non-determinism to small parts of the program. Then we have the stateful model, which can express sequential object-oriented programming. Uh, it is no longer declarative, and it has memory, essentially. And,
Essentially, yeah.
and then we have shared state concurrent model. So this is the declarative model, um, extended with both explicit state and threads. This model contains concurrent object-oriented programming. This concurrency is more expressive than the declarative concurrent model since it can use explicit state to wait simultaneously on one of several events occurring. This is called non-deterministic choice. Reasoning with this model is more complex since there are multiple histories interacting in unpredictable ways. And then we have the relational model, which is for some reason is the last one.
Actually, it isn't. There's another model in chapter 12.
Sure, which is declarative model extended with search, which is sometimes called don't know the non-determinism, although the search algorithm is almost always deterministic. And we have a sequence of choices in there. The search space is explored by making different choices until the result is satisfactory. This model allows to program with relations. It encompasses non-deterministic logic programming in the Prolog style. And then we go to another rule of thumb about using different models together. And then it introduces a concept that I was not familiar with called impedance matching. So impedance matching is one of the most powerful and practical ways to implement the general principle of separation of concerns. So we consider two computation models, big and small, such that the big model is more expressive than the small, but harder to reason in. So like big can be state and small can be declarative. For example,
Yep.
model B could be stateful, yeah. With impedance matching, we can write a program in the model small that can live in the computation environment of model big. So this is essentially, yeah, this is essentially what we did in Karuta, right? A camel environment is capable of doing stateful stuff, but we purposely chose a less expressive model by doing everything immutably, even though the language is capable of going further. We purposely
Uh,
decided to not do that.
Not quite, because we don't have a like larger abstraction which is mutable that we're working within.
We
Uh,
have. It's called the OCaml runtime.
I guess that's one way to look at it, I suppose.
Uh, so the heart of the impedance matching is finding and implementing the right abstraction. This hard work only needs to be done once. Afterwards, there is only the easy work of using the abstraction. Perhaps surprisingly, it turns out that it is almost always possible to find and implement an appropriate abstraction. And so we have some examples here. I'm not going to read all of them, but I'm going to read the first one. Using a sequential component in a concurrent model. For example, the abstraction can be a serializer that accepts concurrent requests, passes them sequentially, and returns the replies correctly. Plugging a sequential component to the serializer gives a concurrent component. So like you are going pedantically, aside from my example on Karuta, going pedantically, this means we make smaller boxes that are using less expressive models, and we fit them in a in the abstraction, which is the basically a cheese with holes, and we fill the holes
Uh,
with things that are less expressive, but the cheese does the power up, does the upgrading. So there is an image here. So yeah, so you have the sequential component, which is less expressive, and you plug it in a box that will give like an extra oomph to make it participate in a concurrent component.
uh, Technically, Erlang does something kind of similar, right? Where,
There is an example of Erlang in here.
yeah, like in the OTP, you tend to
Here
write
you
pure
go.
functions, but then, yeah,
A typical Erlang abstraction takes a declarative program written in a functional language and makes it stateful, concurrent, and fault tolerant. So this is essentially when you upgrade a function to a process.
yeah,
So very good example. We are doing Mahjong, so we know this for a fact. It's definitely the case. You write a function and you add some clothing to the function that allows it to do more stuff than a normal function, such as having a queue for messages, for example. And then we go, yeah, this is out of order than what I read. The Haskell came first before, which makes way more sense. But this is
I
essentially
guess,
explaining,
I guess that's why they flipped it in the new edition.
yeah, so this is essentially explaining a little bit of Haskell. There is one pedantic thing that I really disliked. Let's
Hmm.
see if I can find it. Yeah, strongly typed means that the types of all expressions are computed at compile time and all function applications must be typed correct. I don't think this is right. This is statically typed.
Yeah, this is statically typed. That is, yeah,
Yeah, in the new version, I think strongly is in quotes.
which is better. I agree. Yeah.
Yeah, I'm not gonna double check on that, but I'm fairly certain that I have no idea what they're talking about. Like this is such a silly mistake for these people on this type of level. And then it comments about the monadic style, which is a set of higher order programming techniques that can be used to replace explicit state in many cases. The monadic style can do much more than just simulate state. We do not explain in this brief introduction, but we refer to any of the many papers and tutorials written about it. And then it explains a little bit of Haskell syntax, which we're not going to go through that. You know that. I know that. Um, and then it talks about the evaluation order, right?
Yeah.
Which is the normal order, which means that you're going to evaluate reduce the leftmost expression until it is a function, substitute arguments in the function body without evaluating them, and then reduce the resulting expression. Very normal stuff.
I see what
Um,
you did there.
what?
Very normal stuff when
No,
talking
no,
about normal
it
art.
was not on purpose. It was not on purpose, but I'm glad. Okay, now and then it talks about something that I want to talk about, which is the difference between laziness and non-strictness. Since arguments to functions are not automatically evaluated before function calls, we see that Haskell function calls in Haskell are non-strict. Although not mandated by the Haskell language, most Haskell implementations are in fact lazy. That is, they ensure the expressions are evaluated at most once. We're going to have a separate chapter to talk about non-strictness, so I'm going to just go with the flow. Yeah, 492 here. Optimizing Haskell compilers perform an analysis called strictness analysis to determine when the laziness is not necessary for termination or resource control. Functions that do not need laziness are compiled as eager strict functions, which is much more efficient. And then we have more examples on how to read it. We're not going to go through that. We have function composition, which is nice. We have querying by default in Haskell, which is different than OS. The map arguments are also flipped in comparison to OS. We also have polymorphic types, and there's an example of a binary tree. Nothing too special. Um, and then it talks about querying again. And then we have type classes, which is to generalize the function's behavior to a particular set of constraints. So we can generalize this lookup function that is particular for this being tree to a more general version of that that puts some constraints on the type variables a and b. Well, in this case only a to be ordered. And
Yep.
type classes also gives us overloading, which a lot of some people dislike. Uh, and type classes are supported by functional languages such as Clean and Mercury. Other languages including ML and OS can achieve a similar overloading effect by using functors. Yeah, this is the parallel, right? So to achieve modular, modularity in the sense of reusing functions and overloading of the functions to different types, you use type classes in here, and for ML and OS you use functors.
Yeah. Basically, this goes a little bit into implementation details, but the way GHC at least implements type classes is it actually adds an extra argument to the functions that require a type class, which
Yeah,
is basically a dictionary of methods.
yeah,
And you can kind of do that manually in ML by just passing around modules as arguments because modules are values.
yeah, yeah. I've seen that before in the Haskell channel in Discord server. It is that like that. We can do the same generalization in factorial, although in factorial this is definitely, well, I mean, yeah, this is definitely not as useful as the lookup, but well, you can do it. Uh, wait, there isn't oh no, it's 492, so we're going there. Cool. So now we're gonna go to advanced topics, the declarative concurrent model with exceptions, which is just not declarative, but um, so yeah, failed value, uh, which handles the interaction between exceptions and by-need computation. Let's investigate how exceptions can make the model non-declarative. There are two basic ways. First, to be declarative, component has to be deterministic. If the statements of these two binds are executed concurrently, then execution is no longer deterministic. One of them will fail, but which one will fail can vary. The exception is a witness to this. It is raised on a unification failure, which means that there is potentially an observable non-determinism. The exception is not guaranteed of this. For example, executing x1 and x2 in order in the same thread will raise an exception, yet x is always bound to 1. But there are no exceptions, then execution is surely deterministic and hence declarative. But if there are no exceptions. Um, you also have domain problems, such as division by zero. This is also can raise an exception. The exception indicates that an operation was attempted outside of its specification. From the point of view of semantics, there is no guarantee of what operation has done. We could have done anything. Well, I guess this always also depends if you're talking about dependent types included in the party or not, but fair enough. Again, the operation has potentially become non-deterministic. We say that the declarative concurrent model is declarative modulo exceptions. It turns out that the declarative concurrent model with exceptions is similar to the shared state concurrent model of chapter 8. So what do we do when an exception occurs? Well, we can have a catch on it. Um, and then we can use the try catch to put it back the deterministic behavior, which we did in here. So yeah, for example, if a component executes x1 and x2 concurrently, then the minimum it has to do is catch the exception by putting a try around each binding and encapsulate x so its value is not observable from the outside, which is just a pain in the fucking ass.
Yeah.
So then we're now gonna mess around with the bind need. Let us see how to send this idea to bind need computation. What happens if the execution of a bind need trigger cannot complete normally? In that case, it does not calculate a value. What should happen if a thread needs X? Triggering the calculation causes a failure when attempting the binding AB. Yeah, because A is already this, you're binding it again. It is clear that X cannot be bound to a value since the binding computation is not able to complete. On the other hand, we cannot simply leave X unbound since the thread that needs X expects a value. The right solution is for that thread to raise an exception. To ensure this, we can bind X to a special value called the failed value, which in my opinion should be called default value.
It's not really a default though, because you never actually read it.
But that doesn't matter no, because it's just called default because if the concurrency explodes, like in this example, we have a default value already there, waiting for us.
No, it's not a default value because you can't really use it as a value. If you try to read it,
But you
like,
can't use the failed value either.
but you can't use the failed. Oh, you're talking about avoiding the failed value.
No, I'm talking about just naming this better.
No, but the point is, it's not a default value because it's not actually a value that you can use.
But you can't use the failed value either. That's my understanding. We're not going to use this for anything. We're just putting this here because we need this to be bounded to something.
Well, technically, it is used for something, but you can't use it directly, I guess, is the point.
But, well, even if that's the case, why? Well, I guess failed has a slight advantage in this case because the failed in the name means that this failed.
No, it also means that if you try to read it, you actually throw an exception instead of getting a value.
No, but
That's
we
why you
already
can't use it.
no, but we already failed. It's in the past because this means that this bind failed, right?
Well,
That's
yes,
what
if
this
the
means.
by need, yeah, if the function inside of by need throws an exception, the x will be left unbound, right? Because, well, the computation didn't finish, basically.
It creates a failed value that encapsulates the exception cannot calculate. Yeah, so this exploded, so we bound x to failed value. So
Yeah, and anybody that tries to use x will raise the same exception, basically.
yeah, any threads that attempts to use x will raise the exception cannot calculate. Any partial value can be encapsulated inside the failed value. With failed value, we can define a robust version. Okay, so that's why it's not default, because we are actually using a partial value encapsulated inside of the failed value. Okay. We can define a robust version of bind need that automatically creates a failed value when a bind need computation raises an exception. So we have a try catch that tries to do the binding, and if it failed with the catch, we just put the failed value here, which is kind of weird in retrospect because this looks like a function, but it is not a function. And we're just
Well,
passing the exception, like bubbling up the exception.
oh, yes, but you're binding the exception to a variable, right? So that it actually is rethrown when the variable is when you try to read it, right?
Yeah. Um, and then we extend the kernel language to work with that. Okay.
Can I just say, just a quick aside on language design? I can see why they did this, but I don't particularly like this solution.
Well, I don't particularly like that we are making the declarative model non-declarative just to like exceptions are the culprit. Uh, like I understand why we have exceptions because we don't want the program to blow up. But given that the majority of the time that we're gonna have exceptions in the declarative model is due to programmer error, just skill issue, man. Like I'm not saying this is always true, but the majority, I think the book even acknowledges this. In the declarative model, having an exception of this kind is usually a programmer error. So I don't know. Like it seems a
Uh,
lot of extra work to count for to fix that.
well, the point is this model will be used as a foundation later to like build the other models. So the other models have exceptions. So at some point you have to interact with them.
That's
But
fair.
that's not really the point. The point is I don't like this solution because suddenly, if you try to read a variable, you can just throw an exception randomly if you bind it to a failed value. Like a variable no longer represents a value necessarily. It can also represent an error, which is weird.
Okay, that's a fair argument, I would say. This is opening the hell gate to cursed possibilities, essentially.
Yeah, I probably wouldn't do lazy execution like this, like tied to variables directly. Because if you do it, you're kind of forced into having failed values, and that doesn't seem like good language design.
Well, okay, now we're gonna go talk more about lazy execution, which I'm still. Is it gonna talk? Yeah, it will talk about what I want to talk about. Cool. So, lazy design issues. When designing a new language, what is the role of laziness? In reduction, order, and parallelism. Modern functional programming languages are simplified by Haskell, often use a variant of laziness called non-strict evaluation. So, language design issues. Should a declarative language be lazy or eager or both? Should a declarative language be a subset of an extended non-declarative language? Limiting a language to one computation model allows to optimize its syntax and semantics for that model. For programs that fit the model, this can give amazingly concise and readable code, like Haskell and Prolog. Um, yeah, I actually need to check this out. So there is a language called FP, which is hilarious. Carried this to an extreme with a special character set, which paradoxically reduces readability. This is not a surprise at all. However, as we shall see in section 47, many programs require more than one computation model. Yeah, so then he talks about the pros and cons of having of laziness and eagerness.
Wait, you didn't know about FP?
I didn't.
That's surprising, actually.
I never heard of a language called this before.
It's it's the Bacchus language.
Wait, the one from his paper?
Yeah,
Well, then I do know, but I didn't remember that Bacchus gave it this name. Wait, I think we are talking about different papers. Which paper? No, it is
yeah,
it is
that
the paper. It is Can
yeah.
Programming Be Liberated from the Wrong Norm and Style. I didn't Yeah, I didn't remember that the language. Yeah, it's 20-ish pages. This paper. I read it at least 2 times, and there is a section of the language design that he's talking about something that is APL-ish like language. But I didn't remember that the name would be so boring. Okay, okay. Yeah,
Well,
this section is preluded by an acknowledgement that APL was in the right direction. I also remember that. And yeah, yeah, this paper is very good. This paper. This paper is very good, which is also astonishing because the co-creator of Fortran acknowledged that we should have done better. That's very humble and very respectable. Anyway, okay, so I do know this language. I lied. For programming in the small, designing eagerness is important when execution complexity is an issue. This is a very classic complaint about laziness. It makes complexity analysis worse. But on the other hand, laziness is important when designing algorithms with persistence that can have multiple coexisting versions. Uh,
Okazaki mentioned.
yeah, we find that a good approach is to use eagerness by default and put laziness explicitly. And we have the Okazaki mentioned. For programming in the large, eagerness and laziness both have important roles when interfacing components. We've seen this with the dynamic linking example as well.
Yep.
There are basic ways to control execution, either to produce, yeah, then he talks about the producer and consumer example again. And then the final conclusion is that the declarative language intended for general purpose programming should support both, with eager being the default and lazy available through a declaration. If one is left out, it can always be encoded, but this makes programs unnecessarily complex. So now reduction order and parallelism. So now it goes back to talking about the order of reduction. So we talk again about normal order, which is you don't evaluate the arguments if they are not necessary. But then it's going to introduce the applicative order reduction, which means the opposite. So you are evaluating the arguments before doing the call of the function. So in the expression this evaluates both f2 and f3 before evaluating f1. With applicative order reduction, if either of these goes to a bottom, we get a bottom. This is true even though the results might not be needed at all, such as in the const function, for example. But we say that applicative order reduction is strict. Yeah, so this is also very interesting. The laziness is also kinda ish related to the order of or the reduction order, because if you are doing normal order, you have a flavor of laziness because you are not evaluating the arguments if they are not needed at that moment. And in the applicative order, you're doing the opposite, which is you are evaluating them regardless of their usefulness, which is why it's related to it being strict. Uh,
Can I just say I really like the last paragraph in this subsection here?
for all declarative programs, you can prove that all reduction orders that terminate give the same result. Yeah, this is like I'm very happy that exists people that are way smarter than me to prove this. This result is a consequence of the Church-Horster theorem, which shows that reduction in the lambda calculus is confluent. Reductions that start from the same expression and follow different paths can always be brought back together again, which is poetic. We say this in another way. Changing the reduction order. Yeah, this is the same sentence from the new version, and it still bothers me. Changing the reduction order only affects whether or not the program terminates, but does not change its result. But if the program doesn't terminate, the result is bottom. If
No,
it
no, 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 no,
terminates,
no.
it's not bottom.
No, no, no. If the program doesn't terminate, it has no result yet.
It's bottom.
No, no, bottom is not a value. It's not a result. It's a non-result.
Yeah, that's what bottom represents. If you have a computation that doesn't halt, we call this bottom. So this contrast that is
But a
trying to make here,
computation is not its result.
I'm not saying it is. I'm just saying it's saying here that changing the reduction order only affects whether the program terminates. But the effect of terminating or not will change our answer of what's the result of the program. So that's what's confusing to me about this sentence. It does change its result. We can also prove that normal order reduction gives the smallest number of reduction steps when compared to any other reduction. This probably is less of an impressive proof because this is very intuitive, right? If you are using normal order, you're naturally going to reduce less things because you're only going to reduce them if they are actually necessary to be reduced, given that we don't evaluate the arguments of a function before evaluating the function, and maybe the function ignore all the arguments.
That is true.
So I'm not saying this is the proof, so please don't kill me, mathematicians. But I am saying that this is a very intuitive conclusion that it's aligned with the mathematical proof. And then we're going to talk about what I want to talk about, which is non-strict evaluation. So I was kind of it's very confusing at first to think about there is laziness and there's non-strictness. So what is the fucking difference? So I could count two differences, and I would like to confirm if I got it.
Okay.
The first one is if we're going to calculate the result once or more.
That is a difference, yes.
And the second is the number of reduction steps.
Well, that's kind of a consequence of the first difference, but yes.
Yeah, so that's it. Those are the only differences between the two terms.
Yeah. As an example, actually, algol is non-strict, but is not lazy. So if you try to use the same argument twice, you're actually going to compute it twice.
Mm. We mention non-strict evaluation because it is used in Haskell, a popular functional language. The difference between non-strict and lazy is subtle. A lazy language does the minimum number of reduction steps. A non-strict language might do more steps, but is still guaranteed to terminate in those cases when the lazy language terminates. To better see this difference between lazy and non-strict, consider the following example. So we have a local function, a local bind, sorry, and then we have an x equals the f apply 4 applied to f, and then we do x plus x. In a non-strict language, f4 may be computed twice. In a lazy language, it will compute it exactly once when x is first needed and the result reused for each subsequent occurrence of x. A lazy language is always non-strict. Wait, but not the other way around. Yeah, this is what confuses me. If a lazy language is always non-strict,
But there are non-strict languages which are not lazy,
yeah,
like
but why
algol.
why is a lazy? No, your example makes sense. This first sentence to me is my problem.
Well, Haskell is non-strict and typically lazy, right?
Yeah, so this means that non-strict is one or more, and this is one. So this is why this is a subset. Yeah, a
Yeah,
subset of this.
yeah.
Okay. And in a parallel processor, right? So, for example, during the execution, we might start executing on a available processor even before we know whether it's really needed or not. This is called speculative execution. This is very common subject in processor, like
Hardware
operating
design.
system and hardware courses in programming, well, computer science related courses. Like this is always a topic in there. And there's actually a surprising amount of hardware that participates in this thing. If later on we find out that this is needed, then we have a head start in its execution. If it's not needed, we have to flush it. This might waste some work, but since it is another processor, it will cause a slowdown. Well, it will not cause a slowdown for the entire system. It will cause a slowdown to that particular process CPU. A non-strict language can be implemented with speculative execution. This makes sense. Non-strictness is problematic when we want to extend a language with explicit state. A non-strict language is hard to extend with explicit state because non-strictness introduces a fundamental unpredictability in the language execution. We can never be sure how many times a function is evaluated. In the declarative model, this is not serious since it does not change computation results. It becomes serious when we add explicit state. Functions with explicit state can have unpredictable results. We can never be sure how many times a function is evaluated. Um, Lazy evaluation has the same problem, but to a lesser degree. Evaluation order is data dependent, but at least we know that a function is evaluated most once. Wait. Ah, I see the problem. Is because if if you do this and f is doing some mutable shit, because of the non-strictness, you don't know how many times this.
Yeah, yeah, you see the problem, yeah.
The solution using the declarative concurrent model is to make eager evaluation the default and lazy evaluation require an explicit declaration. The solution using Haskell is more complicated. To avoid explicit state and instead use a kind of accumulator called a monad. The monadic approach uses high order programming to make the state threading implicit. Um, the extra arguments are part of function inputs and outputs. Will this book talk about CPS?
I don't think so, no.
That's very sad. They are threaded by defining a new function composition operator, which is the bind. Data flow variables as communication channels. Yeah, so this is also something that we talked about it before, which is the fact
Yep.
that data flow variables also signal things. There is a correspondence between operations on data flow variables and operations on a communication channel. We consider a data flow variable as a kind of communication channel and a thread as a kind of an object, which makes total sense. Then, binding a variable is a kind of send, and waiting until a variable is bound is a kind of receive. Those two are fine to me. I have problems with these two. Okay. Um, on communication channels, send and receive operations can be asynchronous or asynchronous. This gives us four possibilities in all. Can we express these possibilities with data flow variables? Two of them are straightforward. Binding a variable corresponds to an asynchronous send. Makes sense. The binding can be done independent of whether any threads have received the message. Perfect. Waiting until a variable is bound corresponds to a synchronous receive. Also perfect. What about the other two to compute this table?
Yeah.
Asynchronous receive means simply to use a variable before it is bound. So means creating a partial value.
Basically, yeah.
For example, the variable can be inserted in a data structure before it is bound. Of course, an operation that needs the variable's value will wait until the value arrives. So far, so good. I have a problem with this one. Synchronous send means to wait with binding until the variable's value is received. What the fuck that means?
Um, have you ever studied CSP, communicating sequential processes?
No?
Well, we have used Go, right?
Yeah?
Um, well, in Go, you have this concept of a channel, right?
Yeah?
What happens if the channel has no buffer and you try to send a message?
I don't remember, but there will be some special behavior about that.
Basically, you're gonna block until there's a reader available.
You're gonna block until there's a reader available.
Yeah, that's a synchronous send. Basically, if you're doing CSP, if you're using channels in that sense,
You only
and
produce something if there is an acknowledge of a consumer.
yeah, basically, if you try to read and there's no producer, you block. If you try to send and there's no reader, you also block. You need to have both a reader and a sender at the same time for the computation to proceed, you see?
Mm.
In this case, both the read and the send are synchronous.
Ah. Okay, so sync send, we do a by need on it, and then we wait on sync. Ah, okay, this makes perfect sense with what you just described. If this is needed, and then we're gonna unblock ourselves by doing this means that somebody is on the other side.
Yeah, exactly.
Doing sync send sends M on a channel X and waits until it has been received. Ah, now I got it. Communication channels sometimes have non-blocking send and receive operations. These are not the same as asynchronous operations. The defining characteristic of a non-blocking operation is that it returns immediately with a Boolean result telling whether the operation was successful or not. So this is what? Futures?
Wow, this is basically talking about the difference between um, waiting for something to happen versus not waiting. And then in this particular point, it talks, okay, when you're not waiting, then either you are guaranteed that it succeeds or you are not. And if you are not, this is just non-blocking. It's not quite the same as asynchronous, right?
Yeah, but I
An
think
example,
yeah, but this is a
an
future.
example that not really. An example that comes to mind actually is from the previous book. Remember when Gabriel talked about syscalls and how in Unix you
Yeah,
can
yeah,
have a
yeah, yeah.
syscall that fails, right?
Yeah, but I
So,
think I think this is futures because if you do the future, you have a poll, and the poll tells you if you're done or not. That's non-blocking.
well, that is non-blocking, yes, but also it's slightly, it's not telling you whether it's not telling you whether a particular operation succeeded or not. It's just telling you whether the future is done or not, which is a slightly different
Yeah,
notion.
yeah, but you can make them the same. I'm not saying they are the same, but you can have a particular implement example that those two things mean the same,
Well, you could, yes.
and that's what I was thinking. But you're right; they are not exactly the same, like pedantically the same thing. With iterable variables, a non-blocking send is trivial since a send is always successful. Wait a moment.
Well, in this case, it's assuming that the variable is initially unbound, right? Yeah, you can always bind it in that case.
But how does that work? Like,
You just bind the variable to a value.
okay, a non-blocking receiver is more interesting. It consists in checking whether the variable is bound or not, which we already discussed before about adding the observable non-determinism.
Is that, yeah.
Is that more on synchronization? And I have seen threads that communicate through shared dataflow variables. When a thread needs the result of a calculation done by another thread, then it waits until this result is available. We say that it synchronizes on the availability of the result. Synchronization is one of the fundamental concepts in concurrent programming. We first define precisely the basic concept called the synchronization point. Consider threads doing each doing a sequence of computation steps. T1 does this, T2 does this. The threads actually execute together in a global computation. This means that there is one global sequence of computation steps that contains an interleaved version. There are many ways that the two computations can be interleaved, but not all interleavings can occur in real computations. First, because of fairness, we've seen this before about starvation. If the threads depend on each other's results in some way, then there are additional constraints on the synchronization points. Synchronization is a local property that is enforced by operations happening in the threads. So then we have implicit synchronization and explicit synchronization. Implicit means that the program, the it's not gonna be in your on your face how the synchronization is being done. The program will read as a normal program. Explicit
Yep.
synchronization means the producer and consumer solution that we've seen before. That we wanted the consumer. Or is it the buffer, the bounded buffer, or the consumer one? I don't remember.
Yeah,
But
it's the buffer example.
yeah, so that is explicit, which is a pain in the fucking ass. So then we have supply-driven synchronization, attempting to execute an operation causes the operation to wait until its arguments are available. In other words, the operation synchronizes on the availability of its arguments. This waiting has no effect on whether or not the arguments will be calculated. If some other thread does not calculate them, then the operation will wait indefinitely. And we have demand-driven synchronization, attempting to execute an operation causes the calculation of its arguments. So this is again, we've seen this before in the producer and consumer example where we did supply-driven first, and then we went to the demand-driven change, the consumer dictating the thing.
Yep.
Table 4.5 shows the four possibilities. All four are practical and exist in real systems. Explicit synchronization is the primary mechanism in most languages that are based in the stateful model. Implicit synchronization is the primary mechanism in most languages that are based on the declarative model, such as Haskell and Prolog. All four possibilities can be used efficiently in the computational models of this book. We find that concurrent programming is simpler with implicit synchronization than, well, who finds the opposite? What are they smoking? In particular, we find that programming with data flow execution makes concurrent programs simpler. Even in a stateful model, like the one in the future, data flow execution is advantageous. After comparing languages with explicit and implicit synchronization, these people came to the same conclusion that data flow variables are spectacularly expressive in concurrent programming as compared to explicit synchronization, even without explicit state. This expressiveness is one of the reasons why we emphasize implicit synchronization in this book. And then we go to like okay, they're just that good. They're very good. Okay, so
Yeah.
they are very nice. They are very fucking nice. I don't know how bad in terms of implementing the runtime for these things is, but if I had a magic wand and I just cast a spell and I can have it, I would definitely do that. Okay, so what can we use dataflow variables for? If that is not even like very explicit on our faces. It is powerful primitive concurrent programming. It can be used for synchronization, communication between concurrent computations. It removes order dependencies between parts of a program, thus giving you declarative concurrency. To be precise, it replaces static dependencies by dynamic dependencies. This is the basic reason why data flow computation is useful for parallel programming. The output of one part can be passed directly as input to the next, independent of the order in which the two parts are executed. Yeah, very nice. Powerful primitive for distributed programming, which we haven't seen before. It improves latency tolerance and third-party independence. A data flow variable can be passed among sites arbitrarily. At all times, it remembers its origins. When the value becomes known, then the variable will receive it. The, well, not only that, everybody looking at the variable will take notice.
Yep.
The communication needed to bind the variable is part of the variable and not part of the program manipulating the variable, which is also this is a very subtle difference. Like,
It is.
the variable by itself, you have the capacity of just trying to look at it, you already have the data flow advantage. You don't have to pick the mutex and call the lookup function on it.
Uh, it's not even about mutexes specifically. This is a sneak peek for when we go to chapter 11, which is about distributed programming. It's even more powerful.
No, no, no. Yes, but I'm just taking the mutex example because this is not true with the mutex. With the mutex, there is a separate portion, which is the function
Yeah.
that does a lookup, that needs to be called, even though you have the mutex on your hand.
Yeah.
So that's a very subtle difference, but I find it kind of like um, surprising. It makes it possible to do declarative calculations with partial information, partial values. Um, it allows declarative model to support logic programming. That is, it is possible to give a logical semantics to many declarative programs. This allows reasoning about these programs at a very high level of abstraction. Um, and well, they were originally called logic variables, apparently.
Yep.
And then there's the stateful versus stateless. So a dataflow variable is stateful, which with the interpretation that we had before.
Yeah.
So you have multiple places looking at it, and that gives a little bit of a feeling of a state. And it's stateless because binding is monotonic.
Yeah. You can add
So
more information, but only add more information. You cannot change it.
yeah, uh, assume the variable is bound to a partial value. Later on, more and more the partial value can be bound, which amounts to binding the unbound variables inside the partial value. But these bindings cannot be changed or undone. So that's why it's monotonic, it only grows. The stateless aspect can be used to get some of the advantages of declarative programming within a non-declarative model. For example, it is possible to add concurrency to the declarative model, given the declarative concurrent model of this chapter, precisely because threads communicate through shared dataflow variables. Yeah, so this is a really powerful concept. Like I told you before, I feel really dumb by not knowing them before. But I guess it's always better later than ever. So then
Yeah.
we go
Data
to
flow variables are great.
so then we have futures and line structures. So a data flow variables in this book are but one technique to implement data flow execution. Another quite popular technique is a single assignment variable. This is a mutable variable that can be assigned only once. This differs. Yeah, this is kind of a funny sentence. If you're gonna assign something only once, why does it have to be mutable? This differs from data flow variable in that the latter can be assigned to many partial values. So like you can do multiple like pattern matchings, like destruction of the partial value.
As long as the values are compatible, yeah.
Yeah. Two of the best known instances are futures and I structures. The purpose of futures and I structures is to increase the potential parallelism of a program by removing inessential dependencies between calculations. They allow concurrency between a computation that calculates a value and one that uses the value. This concurrency can be exploited on a parallel machine. Futures were first introduced in Multilisp, a language intended for writing parallel programs. Multilisp introduces the function called future e, where e is any expression. This does two things. It immediately returns a placeholder for the result of e, and it initiates a concurrent evaluation of e. When the value of e is needed, a computation tries to access the placeholder, and the computation blocks until the value is available. We model this as follows in the declarative concurrent model. I don't remember
By the
what
way,
this is. Do you remember?
that's um that's a read-only view on X.
I see.
So yeah, you can use X to read it, but if you try to bind, it's actually going to block until somebody else binds it first before you can proceed.
Wait, it blocks until somebody else binds it.
Yeah, because like if you try to bind it and it's a read-only view, you can't really write to it. So you have to wait until it's determined,
I
and then you
see.
just do normal pattern matching on it,
I
basically.
see, I see, I see, I see, I see.
By the way, Clojure also has futures, because why would it not have them?
Sure. A future can only be bound by the concurrent computation that is created along with it. This is enforced by returning a read-only variable. Multilisp also has a delay construct that does not initiate any evaluation but uses binary execution. It calls evaluation of its argument only when the result is needed. An AI structure, an incomplete structure, is an array of single assignment variables. Individual elements can be assessed before all the elements are computed. So this is a stream. I structures were introduced as a language construct for writing parallel programs on data flow machines. For example, the data flow language ID. I structures are
Actually,
also go on.
actually, id, as in from the uh, Freud's id, the
Ah, okay.
yeah that reference.
I structures are also used in PH, parallel Haskell, a recent language design that extends Haskell for implicit parallelism. An I structure permits concurrency between a computation that calculates the array elements and a computation that uses their values. When the value of an element is needed, yeah, but you don't need this. Like if you, what's the difference between this and a data declarative concurrent stream?
This is not really a string though. This is an array. You can do random access on it.
No, you not necessarily because some parts are not done yet.
Well, yes, if you try to access something that's not computed, you block.
Yeah, so that's why I said it works like a stream.
It can. The difference is that it can be computed out of order. Like somebody may
Ah,
complete
so
element
why is that not
12.
mentioned in here?
Well, it's an
Fuck.
array. It's an array of single assignment variables.
Yeah,
Yeah,
that.
that's not very explicit. I agree.
Okay, so that's the difference between. This is why you would use this instead of a stream.
Yeah,
Okay.
somebody may compute element 12 before element 0 even starts.
Yeah. Okay. Now I got it. When the value of an element is needed, then the computation blocks until it is available. Like a future and a read-only variable, an element of an I structure can only be bound by the computation that calculates it. There is a fundamental difference between data flow variables on one side and futures and I structures on the other. The latter can be bound only once, where data flow variables can be bound more than once as long as the bindings are consistent with each other. Two partial values are consistent if they are unifiable. A data flow variable can be bound many times to different partial values as long as the partial values are unifiable. We've seen this before. Multiple readers are each allowed to bind the list stale since they bind it in a consistent way. Whew! Okay, so now for 10 historical notes. So what is important in here? Uh, yeah, this is just talking about like the history of
data flow variables, basically.
Yeah, the history of data flow variables. I don't have anything to highlight in here, I believe.
It's kind of funny that they actually came about from like logic and constraint programming and not from the imperative world, which is the one that tends to emphasize concurrency a lot, right?
I don't think so. That doesn't surprise me at all. Because in order to reach the conclusion that we should have data flow variables, that's a very non-imperative thing, because that will put a lot of burden on the runtime, and imperative folks hate to have a big and complex runtime. In order to
Uh,
conclude this, you need folks that are focused on things that are highly abstract, such as constraint programming. They are the ones that are actually okay with putting a little bit more burden on the runtime in order to have nice constraints and properties available. So you just see like there's a reason why the imperative folks are not crazy about dependent typing. It's not only because of the ideologies portion of it, but it's also because in their point of view, they want the least amount of runtime overhead as possible. So they want to do all things by hand. That's kind of an extension of the whole memory allocation by hand.
hmm.
So that doesn't surprise me at all that the folks that actually got to that point was the folks that are more mathematical and more high abstraction heavy, such as constraint programming. Those are the ones I would expect to reach this conclusion that hey, maybe data flow variables are actually nice. Uh,
Well, they are. They really
uh,
are.
yeah, so that I'm actually not surprised. Uh, the basic concept of determinate concurrency was defined by Kahn. The existence of the data-driven model is implicit in the work of this guy. The demand-driven model is related to the model that they talked about. The contribution of this book is to place these models in a uniform framework. Binding synchronization is based on the concept of needing a variable, because need is defined as a monotonic property. This is quite a general declarative model that has both concurrency and laziness.
Yeah. This is really nice. I like this chapter a lot.
I'm very thirsty. Okay. Okay, so what's plans for next time? So we have 2 pages of 5.1, cool. And then we have 3 pages of 5.2. And then we have 9 pages of 5.3, which is still fine. How many pages for 5.4? 5.4 is actually 15 pages. So okay, so we rather do 5.1.2.3 or 5.1.2.3.4.
Uh,
One of them is 17 pages, and the other one is 35.
let's do 1, 2, 3 because we're gonna get into concurrency now. So yeah,
Cool.
like actual non-declarative. Let's do non-deterministic stuff. Concurrency. Um, Even though message passing is really well behaved compared to like shared state. Um, I'm not sure actually. Although, yeah, I am inclined to do 1, 2, 3 to be honest.
Yeah, so we settle on 1.2.3. I'm gonna finish the recording now.